Okay, good morning. We're starting on chapter 4 today, graphing linear equations and functions. And our first section is just a bit of review on coordinate planes, really. But we will add the little extension on transformations, and you'll see that at the end of this lesson. So we're just talking about the words that go along with graphing. So we're dealing with a coordinate plane. So we're going to kind of create a little coordinate plane and talk about the pieces of that. Okay, so I'm going to pause this and take down, make a little coordinate plane. Okay, how many dimensions are revealed in a coordinate plane, everyone?
4.
How many dimensions?
4.
2 dimensions. I heard 4, but I think you're jumping to, you know, how many areas, right? So it's a two-dimensional graph. So if we think about it, there's a number line that is horizontal. And how do we label the horizontal number lines, Sophia? And so you're saying it is the, what? It's the x-axis. Good. The x-axis. And then we have a second number line, and it is called the
y-axis.
Y-axis, right. Good. And then there are quadrants, and I think that's why I heard people say 4 dimensions, but not really dimensions. It's 2 dimensions. It's a flat figure, like a plane. It's an infinite plane when we have these arrows at the end of our axes, which we do need to have, so make sure you have them. I allow you to label them just x and y without writing the word axis. You might end up with a teacher who asks you to write the word every single time. I had a teacher like that in high school. So it was a lot of writing the word axis. These are the 4 areas, the quadrants, right? Where is quadrant 1? Quadrant 1. Anderson? Okay, so right here, quadrant 1. So quadrant 1 is positive in the x direction and positive in the y. It's positive, positive when we look at ordered pairs. So then the next question, and who knows the answer? Raise your hand if you know where quadrant 2 is. You know where it is? You remember? So do we go clockwise, 1, 2? Or do we go counterclockwise, 1, 2? Ryan? He thinks bottom right. Who agrees? Thumbs up if you agree. And there's just not too many people voting here. Anderson, where is it? Upper left. Good job. We actually have to move counterclockwise when we're naming these quadrants. So the y values are still positive. The x values are what become negative. That's our second quadrant. And then we can just flow around from there. So quadrant 3 is negative x and negative y values. Quadrant 4 is right underneath quadrant 1. Positive x values, negative y values. Who remembers what this point is called right here? Which has a value of 0, x, and 0 in the y. It's the point of, say it, good, origin. So you might label that point of origin right there. Point of origin means the beginning, right, where we start. Okay? So the quadrants are 4 regions of the coordinate plane. Sometimes we work only in one region. Which region is the most commonly found region in a real world situation, Michaela? Quadrant 1. Good. So sometimes we just see that quadrant alone because we don't go negative in time or something like that. We'll see. Okay. So an ordered pair will give us what, Riley? A point, right, on the plane. So we, as a model, we use the letters x and y. Could we have a coordinate plane that uses other letters?
Yes.
What is that famous linear equation for distance? Remember? D equals RT. So we could actually put t on the x and distance on the y. The rate is the slope of the change, so that's where the r shows up there. Okay? So we would have d and t then. Or we would actually have td if we put time on the x-axis. So those letters can change, but most often we're using x and y. So that's what we say. In order to find the coordinates, what must a person do to find the coordinates? So here we have this, I'm going to give you a moment to jot this little figure down again. And we're given 3 points, E, C, and D. We need to carefully identify their coordinates. Anybody want to give a hint on how to find the coordinates? Remember that little phrase that we sometimes use to remember what comes first? A minute.
Walk before you fly, X for Y.
Good. Walk before you fly, X comes before Y. So right now, you might pause the video, try to complete finding the coordinates for these points. Okay, so Bailey, tell us, where is C? Thumbs up if you agree. She says 0, 2. That is correct. Good. So you can fill that in. 0, 2. So when you start at the point of origin, and we walked nowhere and just flew 2. And there we are. C is right on this y-axis. Okay. And how about D? Where is D? Branda?
It's 3 and 1.
Good. So walk 3, fly 1. And where is E? Juliana?
-2, -3.
-2, -3. Everyone happy?
Yay!
Just a second. All right, we're going to now plot some points in the coordinate plane. So we're doing the reverse. This is like a teeter-totter. We just identified where those points were on the last graph. Now you're going to graph a few points, make sure that they're in the exactly perfect location. Okay? So pause the video, do your best, and come on back. Bringing a volunteer up. The first thing I notice as I look at this coordinate plane is there's no scale. So could you fill us in on the scale? Okay, so every blue line there, it does represent 1 if she chooses this, but just a second. The 10 really should be brought right underneath where it is 10, okay? So let's see, whoops. Right there, and then this one right next to it. You could even put a dash where that is. In other words, like this. 10, 10. Let's not have things floating way out there. Okay? It show precisely where it is a value of 10. Because she could choose to go by some other scale. Like if every blue line was 5 units, then down there where she has 10, we would label 50, right? So, and label the letter for that point. And it's a little tough on the smartboard to be as precise as you can be on paper. So even though I calibrated it, she's just labeled, did you label that A?
I got this one A, but it kind
It's
of
just so tiny. Let's back it up a little bit and make it a bigger letter. There you go, good. And that is, you have to write hard on the smartboard, that's a B, okay. And there's your C, and D, good job. Okay, everyone got to the right place? Walking and flying, good. Okay, so let's try graphing a function. So there are 3 quick steps to graphing a function. And we're going to talk about those now. So here is a given function, y minus 2 equals -1/3 x. I'm going to give you a moment to catch up to this point. Has anyone noticed the first thing you might need to do to this function? What's the first thing you might need to do to the function? Right. Good. And we call that putting it into what form? Well, that's advanced, but really for any type of equation, it would be function form. And so yes, you could put it in slope-intercept form too, which is a function form. So what do you have, or how did you isolate y? Added 2, added 2. And we have y equals what? Plus 2. Good. So isolated y value. That is the first step. And that's what it says here. Put it into function form. And then the most basic way of graphing was not using slope-intercept form, even though that is maybe our favorite way. We haven't talked about that yet this year. So what's the most basic way of graphing any function? you have it in function form, and you make a
Table.
table. And then in that table, of course, you have points and you graph them. Okay? So you could make a horizontal table, you could make a vertical table. You could put this function in a table. Let's make a vertical table. X, Y. And what values might a person choose? Do you remember how you chose values for a table? I mean, what's the easiest input in the world usually? Right? 0. So we might put that there. And then we want some negatives and positives. But take a look at the number that's next to the X. That can let you know, or that can kind of give you an idea of what might be easy numbers to plug in. What would be an easy number to put next to the 1/3, negative 1/3, Michaela? 3. Good. Or negative 3. So negative 3 or 3. And so why did you choose that, Michaela? Good. So negative 1/3 times 3 is just, the 3's kind of cancel, quote unquote, right? And you get negative 1. Negative 1 plus 2 is 1, right? So we're just substituting what you chose. If we plug in that negative 3 times negative 1/3 is what?
Negative 1.
Negative times a negative is a positive. It's positive 1. 1 plus 2 is 3, right? If we plug in 0, negative 1/3 times 0 is 0 plus 2 is 2. And then give me another number that we can.
1.
If we plug in 1, we could do that, but it'll give us kind of a fraction, right? Let's plug in 6. If we plug in 6, negative 1/3 times 6, right?
Why 6?
6, because look at 3 goes into 6 how many times?
2.
2, right? Negative 1 times 2 is
2.
negative 2, and then negative 2 plus 2 is 0. So do you start to see a pattern in our range over here? 3, 2, 1, 0. Nice pattern. And that's because we were giving a pattern in the domain as well. Negative 3, 0, 3, and 6. As the domain increases by 3's, the range is decreasing by 1. See that? So what would you predict, what would be the domain that makes sense in this position right here, everyone? Negative 6, right? And what would you predict the range to be?
4.
4, right? Good. And if you plug 4 or negative 6 in, you will end up with 2 plus 2, which is 4. Okay? Good. Now, if you didn't choose these numbers, you will, if you do your math correctly, still get points that are on this line, points that are part of this function, because how many points would be found in this function? How many points does this function have? Infinite. So you choose the x to put in, and you will get a point on this line. It just may be in a different place on the line, right? Okay, we have 5 points. Why is it nice to have 5 points in your table? Zach? Okay, yeah, but how many points are really required to make a line? 2, right? So why would you choose more? To make sure your math is correct. With negatives and positives with other negatives in the equation and so on, people can have a problem and end up with something that doesn't look like a line. But because we are graphing lines right now, you should be able to catch that if you start graphing something like 0, 2, 3, 1, 6, 0, and then let's say you go negative 3 and 1. You're like, wow, this is looking triangular. So probably I did something wrong with my math because this is a linear equation, okay? Which you may or may not know, but this is a linear equation. So we have really negative 3 goes to 3, and negative 6 goes to 4. Okay. Did they give us a specific domain to use? Specific x values?
No.
No. So we could have chosen all of the x values in between these and all of the x values beyond them, right? So do we need to draw the line?
No.
Yes, we do. Because we were not given a specific domain. This is a continuous function. And we need to draw a line with arrows on the end. Okay? Okay, I'm not asking you to draw this, but I want to talk about what happens when you have like extreme numbers in your function. So if you're given a table, be careful with your scale. You might put that little note down, but this is the big question that is a guided practice problem in this section of your textbook. So they're talking here about a presidential election in 1972, and they give you these numbers. It was the first election where 18-year-olds were allowed to vote. The table shows the number to the nearest millions of votes cast in the presidential elections both before and after 1972. So 1972 would be the 0 year. See that? And look at the votes in millions. What happened after 1972? What happened with the votes? Did they increase or decrease?
Increase.
Increased in number. So it seems like allowing 18-year-olds to vote increased the number of voters
That makes sense.
as compared to beforehand. See that? And maybe all voters increased. I don't, older people increased in numbers too. I don't know. The population just increased. But what I want to talk about here is look at the difference between the x values. If we use the top as x values, we could say these are the x's, and then what the number of voters are is the y, right? So when we go to graph this x and y, I have really big numbers in my y values in the range, and I have really small numbers in my x values, the domain. So how does a person graph that then? Emily? Good. So you may use different scales for the x and y axis. You could literally use a scale of 1 in this x direction. So this again would be -10, right? Over here we would have 10. But in the y direction, I need to go to 93, and these are in millions. So I might go by hundreds here. This is 100, which means halfway we have 50 million. Okay? And so when we plot this, again, this is just a note that you may use different scales on your x and y axis. Does everyone understand that? We saw that a lot last year, so hopefully you are comfortable with it. But be careful that you're paying attention to what you have chosen. Sometimes people will choose different scales for x and y, and it makes sense, and then they forget when they go to plot your points. So you have to be super careful plotting your points. Okay? How do you know an equation is a function? Do you remember? We've already talked about this, I believe, this year. Nico.
Each input has one output.
Okay, each input has exactly one output. Good. Okay, don't we have some of these samples already from this year in your notes? Or am I
Yeah.
thinking of 7th grade? Okay, so you don't need to take these down then, because you have some, right? Unless you want to. But let's take a look at this first relation. It's just a set of points, set of ordered pairs. So everyone look at it and decide, is it a function, yes or no, and I'll count you down. You can tell me. Is this a function, yes or no?
Yes.
And you know that because which input?
-1.
-1 occurs twice, and they both have the same output. Okay? Is this a function, yes or no?
No.
And you know that because?
-1.
-1 has two different outputs. Good. Is this relation a function, yes or no?
Yes.
Yes, it is, because you input -1, and what do you get out every time?
2.
2. Even though it looks kind of different, it is a function. And is this a function, yes or no?
No.
No, it's kind of looks like the previous one a little bit, but now each input has a different output. Even though it appears to seem to be a pattern, it is not a function. Okay? Very good. Okay, we're going to talk a bit about transformations, and then we're done. A lot. So a transformation of a figure on a coordinate plane produces an image of some original by doing something to it mathematically. When we operate on points mathematically this way, we say we're applying a rule to the points. Applying a rule to the coordinates of the points, the numbers. Okay? The first transformation we're reviewing today is a translation. Hopefully you remember this from before, but if I take one of these figures, let's take this little triangle right here that I have. I'm going to move everything else off. Okay. If I take this triangle and I start right here, and then I clone it, and I move that triangle from right here just to here. Do you see how it slid? It's like a slide. I mean, it didn't spin or rotate or do anything like shrinking or stretching. It just went down, didn't it? So if we look at this little vertex over here, can somebody give me the coordinates of that vertex right there? What is it? Somebody else. Where is this corner, this vertex? Sabrina? 0, 0. And so now in the new figure, where is that vertex? And right down here is 10. So everyone, what is this value? -9, right? So it's still at 0, but we're now at -9, right? So what did we do to the 0, 0 to get to 0, -9? What did we do? Right? You just subtracted. So translating a figure is adding or subtracting to the coordinates. Okay? If you want to go up or down, you would add or subtract to the y, just like we did. We could add 9, we could subtract 9 from all of the y's, and that's how you slide a figure up or down. If you want to slide the figure left or right, notice we're now adding to the x, or we could subtract from the x. Okay? So a vertical stretch or shrink is a different type of math rule. So look at, if I take this original figure here and stretch it, what do you think the math is behind that? What have I done to each point? What do you think? Zach? You do, you multiply it. We're multiplying by something greater than 1 to stretch it. If I want to shrink it, I can multiply it by something less than 1. There it is, a little shrunk thing. Okay? It's exactly what the smartboard is doing too, mathematically speaking. Okay? And finally, a reflection. Let me just clone this one again. So we have the exact same size, right? We have two triangles of the exact size right here. And actually, the smartboard has a feature that will allow me to rotate or reflect it. Whoops. I'm going to grab that triangle. Here we go. There we go. There's a reflection. So each of the coordinates, let's say this coordinate right here, which would be at 1.5 and 7. 1.5, 7. That point that is opposite it, way down here, is now still at 1.5, but what happened to the 7? It became a -7. See that? So when you reflect across the x-axis, which value becomes the opposite? Zero, 7. I'm approximating this. 0, 7. Came down here and became 0. I'm sorry, not 0. 1.57 became 1.5 -7. So when you flip across the x-axis, which becomes opposite?
Y.
The y coordinate, right? If I take and flip across the y-axis, what do you think is going to happen to the map? I can grab this triangle. There we go. So if I take this and flip it across this axis, do you see that this point up here, 1.57, has now become negative 1.57, right? So when you flip across the y-axis, which value has changed?
X.
The x. It's like they're opposites, aren't they, right? When you take the opposite in the x value, you hop across the y-axis, and when you take the opposite y, you hop across the x-axis. Amanda?
Why are we doing negative 1?